Recent observations of the interstellar object known as 3I/Atlas have reignited scientific curiosity after astronomers detected what appears to be a faint bluish hue developing around the comet. This subtle color shift, while not yet confirmed through multiple independent observations, has drawn significant attention because it represents the third time since the object's discovery that its coloration seems to have changed. Although previous color variations did not persist long enough to be definitively verified, this latest development is particularly intriguing due to the circumstances under which it occurred. Following a rapid and unexpected brightening event while the comet was hidden behind the sun together. These factors suggest that 3I/Atlas may be undergoing complex physical and chemical processes unlike anything typically observed in comets native to our solar system. 3I/Atlas holds a special place in modern astronomy, as only the third confirmed interstellar object ever observed passing through our solar system. Unlike ordinary comets that originate from the Kuiper Belt or the distant Oort cloud, this object is not gravitationally bound to the sun and instead follows a hyperbolic trajectory, indicating that it was born around another star entirely. When it was first detected in early July, it was already moving at extraordinary speed, exceeding 130,000 miles per hour. Such velocity strongly supported the conclusion that it came from interstellar space, having traveled for billions of years before its brief encounter with our planetary neighborhood. What makes 3I/Atlas even more remarkable is the possibility that it may be the oldest comet ever observed by humanity. Based on its trajectory, composition, and the inferred history of its journey, scientists believe it could be more than 7 billion years old, older than our own solar system. This suggests that the comet was formed around an ancient star and later ejected due to gravitational interactions, perhaps with a massive planet or a passing star, sending it drifting through the Milky Way's outer regions. For eons, it would have remained in deep interstellar space, exposed to cosmic radiation, extreme cold, and isolation, before chance alignment brought it close enough to be detected by human instruments. As the comet entered the inner solar system, it provided researchers with a rare opportunity to study material that originated far beyond our cosmic neighborhood. Initial observations showed a relatively typical cometary appearance, with a faint coma and no dramatic color anomalies. However, as weeks passed, astronomers began noticing subtle changes. These included fluctuations in brightness and hints of shifts in color, though early evidence was inconclusive. The real surprise came after the comet made a close approach to Mars at the beginning of October, after which it moved to the far side of the Sun from Earth's perspective. During this period, Earth-based telescopes were largely unable to observe 3I/Atlas due to the Sun's glare. Only a limited number of space-based instruments, positioned at advantageous angles, were able to continue tracking it. While the comet was hidden from most observers, it reached its perihelion on October 29th, passing within about 130 million miles of the Sun. Although this distance is still greater than Earth's average distance from the Sun, it was close enough to significantly increase solar heating of the comet's surface. This heating typically drives sublimation, causing frozen gases to turn directly into vapor and carry dust away from the nucleus, often leading to increased brightness. What startled researchers, however, was the magnitude of the brightening detected just before perihelion. According to a preliminary analysis, the comet's brightness increased by several orders of magnitude, far more than could be reasonably explained by its distance from the Sun alone. Such a dramatic change suggests that an additional process was at work, possibly involving the sudden exposure of fresh volatile material beneath the comet's surface. This could occur if part of the outer crust fractured or collapsed, allowing trapped gases to escape rapidly into space. It was in the same analysis that scientists reported the unexpected bluish coloration. They described the comet as appearing distinctly bluer than the Sun, a notable observation because cometary comet often appear white, yellowish, or slightly reddish due to reflected sunlight and dust scattering. A blue tint, by contrast, typically points to the presence of specific gases that fluoresce or scatter light in shorter wavelengths. Among the leading candidates proposed were carbon monoxide and ammonia, both of which can emit or reflect light in a way that gives a bluish appearance under certain conditions. If confirmed, the presence of such gases would offer valuable clues about the comet's composition and its history. Carbon monoxide, for instance, is a highly volatile substance that sublimates at very low temperatures. Its survival within the comet for billions of years would suggest that 3I/Atlas spent most of its existence in extremely cold environments, shielded from intense stellar radiation. Ammonia, similarly, can indicate pristine material that has undergone minimal thermal processing since the comet's formation. Together, these substances could help scientists reconstruct the conditions that existed in distant star systems during the early stages of planet formation. Despite the excitement, researchers are cautious. The study reporting the blue hue has not yet been peer-reviewed, and no independent observations have conclusively verified the color change. Observing faint objects at such distances is inherently difficult, and instrumental effects, viewing angles, or temporary outgassing events can sometimes produce misleading signals. Moreover, the fact that earlier apparent color changes in 3I/Atlas did not persist raises the possibility that this latest shift may also be transient. Still, even a temporary change is scientifically meaningful. Interstellar objects are expected to behave differently from native comets because they have been shaped by entirely different environments. The surface of 3I/Atlas may be unusually fragile after billions of years of cosmic radiation exposure, making it prone to sudden activity when warmed by a star for the first time in eons. Alternatively, its internal structure may contain layers of volatile material that rarely survive in comets formed closer to their parent stars. As 3I/Atlas gradually becomes more visible again to Earth-based telescopes, astronomers around the world are preparing to gather as much data as possible before the object continues on its outbound path and is lost to interstellar space once more. Every observation, whether confirming the blue hue or disproving it, contributes to a growing understanding of how common such objects may be and what they can tell us about the galaxy at large. Each interstellar visitor is a messenger from another star system, carrying physical records of processes that we cannot observe directly. In the broader context, the study of 3I/Atlas highlights how much remains unknown about the universe beyond our immediate surroundings. Only a few years ago, the idea of detecting interstellar objects passing through the solar system was largely theoretical. Now, with improved survey telescopes and detection algorithms, astronomers are beginning to glimpse these rare travelers with increasing frequency. Each new discovery refines our models and challenges assumptions about planetary system formation, evolution, and the exchange of material between stars. Whether or not the bluish hue of 3I/Atlas is ultimately confirmed, the episode underscores the dynamic and unpredictable nature of interstellar comets. Their sudden brightenings, shifting appearances, and exotic compositions remind us that the solar system is not an isolated island, but part of a vast, interconnected galaxy. As observational technology continues to advance, future interstellar visitors may be detected earlier and studied in greater detail, offering even deeper insights into the shared history of stars, planets, and the wandering remnants that travel between them.